Good morning, everyone. In the last class, we discussed about the Gaussian distribution in general, and 2D and 1D Gaussian distributions also as special cases we have discussed. And now in this class, we will switch or further proceed with making a classification when you have the likelihoods of a function are estimated by Gaussians. So how will be the shapes of those Gaussians? How would be the decision lines of that Gaussians? Instead of directly computing the decision lines, if you are using some discriminant functions, which we have discussed in, I think, one or two classes back. So then what could be the possible functions for those what could be the discriminant functions that you could consider? These are the things that we will discuss in this class and perhaps the class after that as well. Okay. So before going into the actual cases where Bayesian classifier for normally distributed functions, let us together rewrite the equation that we have worked out earlier for the probability density function of multidimensional Gaussian function. Okay, so hope you all are well familiar by this time. Let's call that as density per PDF of x bar. Okay, it's a multidimensional one, 1 by square root of 2 pi. Since it's a x bar is an L dimensional feature vector, you have such L things getting multiplied. Then here in 1D you have sigma square, right? Under root if you are square root if you are writing outside sigma, but here a summation matrix will be there. Since it's a scalar, then you would be, and this sigma representing the variance, you have 1 over 2 here, and determinant is what you take there, and exponential of minus 1 by 2. Well, again, just to get an intuition, the parameter inside your exponential is a scalar quantity. Okay, x minus mu whole square by sigma square. Now you write it as x bar minus mu bar whole transpose into it over sigma square was in the denominator. Now you are bringing it to the numerator itself as a multiplication. So that will become inverse of your covariance matrix into x bar minus mu bar, multiply that. You could also see that the dimensionality of inside one will be 1 cross 1. Okay. Now, this is the expression that we got earlier. Now, what we are going to do is we will do the Bayesian classifier for normally distributed classes. That's what we are going to study and start studying in this class and continue for next 1 or 2 classes as well. The Bayesian classifier, the Bayesian classifier for normally distributed classes. For normally distributed classes. Yes. So earlier, if you recollect how we performed or how we proposed to perform the classification, where let's say what it needs to be done for a given class x bar, what is it that has been done in terms of probabilities? You would be computing the probabilities of
probability of omega 1 by x bar greater than.
very good, right? So essentially you would compute probability of omega I given x bar. You would compute for all I varying from 1 is to omega, and out of this is referred to as which probability?
Conditional or a posterior.
Very good. Conditional or a posterior probability. And among them, you would pick that which has maximum value. So then we also have written expressions for it. Probability of omega I given x bar equal to probability of x bar given omega I into probability of omega I over probability of
X bar.
right probability of x bar. Then anyway you are going to compute maximum, and probability of x bar is anyway same, irrespective of which class you are going to assign to it. That's a constant for across all classes. So what you do is compute that I, right, that maximizes probability of x bar given omega I into probability of omega I. So this is what we are going to maximize. This is what we have arrived at in the previous classes. And what is it known as probability of x bar given omega I?
Likelihood.
Yeah, likelihood probability. Then anyway, probability of what is this one? Probability of omega I.
Higher probability. Higher probability.
Right. This is prayer probabilities. Now, likelihood probability will tell you if I know that a given feature vector belongs to a class omega I, okay, what is the probability? Yeah, this I think I should write here 1 is to m here, because omega 1, omega 2, I'm putting it to omega m, right? Coming back, if I know that if it is given that a feature vector belongs to a class omega I, what is the probability that this feature vector belongs to omega I? That is the probability, likelihood probability. Now, in the whole rest of this class, what we would be doing is we will assume that this has a Gaussian distribution. This likelihood function is Gaussian, has a Gaussian distribution. If that is the case, what would be the boundaries of two classes or the decision planes of two classes? Instead of computing the decision planes right away, if you compute the discriminant functions that we have discussed, because as we have mentioned and as you will see in more detail in the rest of the class, computing these discriminant functions will make our life easier compared to right away working on these probabilities. You will realize it in more detail in the rest of this class as well. Okay, so essentially, if you look at it, you need to essentially compute for each class probability of x bar given omega I into probability of omega I. Okay, now let's say this you compute it for one class, that it be fi of x bar. For another class, fjth class, this let it be probability of x bar given omega j into probability of omega j. Okay, now suppose I want to compute the decision line. Okay, if it is a 1D, you call it decision line. For any higher dimensional classes, you could simply call it as decision hyperplane. Okay, it is in L dimensional space. Okay, so let me call that plane as, let that be Fij of x bar. Okay, how do I get that? This is we discussed in the previous class, but I would like to hear it from you. I give you these two. How do you compute the decision line in between the ith class and jth class? Or if you want me to rephrase my question, what can you say about the value at this decision plane in terms of fi of x bar and fj of x bar? Or what would be the values of fi of x bar and fj of x bar at the decision plane?
They will be equal, sir.
Correct. So what I could do here is I simply compute here fi of x bar minus fj of x bar, and then equate to get the decision line. You simply equate it to 0. fi of x bar, I have already now simply I write this expression. If you want me to write these expressions, for example, function of I of x bar, if you want me to write, the way I could write it is 1 over root 2 pi times L. I'm just rewriting what we have written earlier into determinant of covariance matrix whole to the power of 1 by 2 into exponential of minus 1 by 2 into. Now I am writing it for the ith class. So what I would write here, x bar minus mu I bar. Okay. There will be a transpose here. And then this covariance matrix for ith class. Notice each class can have its own distribution. So this is for the ith class into x bar minus mu I bar. Okay. This is what this is probability of x. This is the likelihood function multiplied with what is the multiplication I would get here? Probability of
Omega I.
that's all. Okay. Hope everybody is clear till here. I just have replaced that likelihood function with the expression, Gaussian expression. Nothing else I did here. Now, we have discussed earlier discriminant function. See, all I need to do is the difference between fi of x bar and fj of x bar should be 0. That means they should be same. Fi of x bar should be equal to fj of x bar. Suppose if I apply a transformation on it, which is monotonically increasing, then maybe if you want, I'll give that also. Let's say I am applying something like gi of x bar. Okay. Some function I am applying on fi of x bar, which is monotonically increasing. Similarly, gj of x bar, some function I have not yet written the function here. I'll write that function here. Then if they are monotonically increasing functions, then how can I find the decision hyperplane? I have gi of x bar. Similarly, gj of x bar equal to something of fj of x bar. Okay. Then I want to find out, and this g is a monotonically increasing function. Monotonically increasing function. Then if I give you, instead of fi of x bar and fj of x bar, if I give you gi of x bar and gj of x bar, can you still find out the decision hyperplane? Right? So as we have discussed, you all know what is monotonically increasing function. I have, for example, here f of x bar is there. Here on the y-axis, I have g of x bar. If my f of x bar value is increasing, g of x bar is also increasing. Right? Then it is called as monotonically increasing function. Now the question is, okay, strictly monotonically increasing also you can consider. Now, yeah. So now the question is, how do you compute instead? If I give you g of x bar instead of f of x bar, how do you consider the decision? How do you compute the decision plane? Or maybe if you want to just think about it, meanwhile, let me pose you another question. What is the monotonical function that you would perhaps suggest here? By looking at the expression that I have for pi of that fi of x bar and all. Okay. So this, if for some reason this is not looking as fi, so let me write it as fi of x bar. What is the kind of monotonical function that you would suggest by looking at the expression that I have for fi of x bar? Right, logarithm. One of you had written there. Okay, so our natural logarithm to the base e is what you consider. Okay, because that would bring this whole expression, no need for calculation of the exponential there. So what you would do here is I'll simply write ln here, which means not natural logarithm to the base e. Okay, that's what has been given. Now, before we attempt at any math here, tell me now, if I give you gi of x bar and gj of x bar for varying values of x bar, how do you know where is the decision plane?
Gij equal to 0.
Correct. That's all, as simple as that. See, monotonically increasing function means what? If you want me to write the mathematical definition of it also, if fi of x bar is greater than fj of x bar, then gi of x bar is also greater than gj of x bar. You do not know relatively if two fi and fj are, if fi is greater than fj, any transformation applied on it also will be greater than the other. Same is with less than, same is with equal. You want a case where fi is equal to fj. That means you just need to define another function gij of x bar, which is equal to gi of x bar minus gj of x bar. And after computing this function, you make it to 0 to get the decision plane. Less than 0 would tell you that that function belongs to the ith class. Greater than 0 would tell you that this function belongs to jth class. What would be the expression for gi of x bar? Let's write that first. Okay, maybe since I need to move down, what I'll do is I'll just copy it and put it there. Not sure what all will come, but let's see. Okay, so this is the expression for fi of x bar. Now, what I would like to do is, if you apply a logarithm on it, that will give me gi of x bar. Now, tell me, what is the value for gi of x bar? Minus 1 by 2 into x bar minus mu I bar whole transpose into covariance matrix into x bar. Sorry, this would just end up here. This won't be there. Just that. Okay. X bar minus mu I bar, right? So that's for exponential. What do I get?
ln of p omega I.
Right. Correct. Please be interactive. Don't so that you find it more engaging for you as well as me. Right. Then what? Minus L by 2 into natural logarithm of
2 pi.
right 2 pi. And then again minus 1 by 2
One-
into natural
ln
logarithm
of
of determinant of the covariance matrix. That is important thing. Otherwise, it will not be a scalar also. Right. Okay. Hope you are clear here till here. Now, you do a similar thing for gz of x bar also. So, if you just for your clarification, I would write that also here. X bar minus mu j bar whole transpose covariance matrix of jth class x bar minus mean vector for the jth class plus the logarithm of prior probabilities of the jth class minus L by 2 into logarithm of 2 pi minus 1 by 2 into natural logarithm of, well, I should have written here the covariance matrix determinant of the jth class. Here I should have written ith class there. See, all you need to do now is actually to see the difference there. That's how the transformation is applied here. Do you see any terms that I could drop here? that I could drop here in gi of x bar and gj of x bar, still I could get when if gi j of x bar, which is defined as gi of x bar minus gj of x bar equal to 0. That means it's a decision hyperplane. Is there any values in the above expressions that I could drop? But still I would arrive at the same, but it is still a monotonically increasing function.
Natural log of 2 pi.
Right. You don't really need those functions. So you could in fact drop this function and drop this function. Still, this would be valid here. Correct? Anyway, that is going to get subtracted. Now, to draw some more inferences here or get insight for these equations and to see what kind of shapes can we expect here and all, let me consider here a special case to further simplify these things. What I will do here is let me make calculations for a two-class problem. For a or not a two-class problem, for a feature vector which has two feature vectors. That means my x bar, I would now write it as x1 and x2. Then of course my mu bar will be also of the same one. I have two feature vectors. This will, let me call it as mu1 and mu2. There is some issue with writing it as mu1 and mu2. If I write it, what is the problem if I write it like that?
It will get confused with the index I and j.
Correct, correct. Very good. So in fact, because I have mu I bar here, each class has a vector of it. So I will write them instead mu I1 and mu I2. Okay. To simplify things even further, what I will do is my summation matrix is equivalent to, again, for a given class I, not summation matrix, covariance matrix is equal to sigma I square 0 0 sigma I square. This is what I would consider. What does that mean again? All class, what how can you infer that? This you could infer that all components of the feature vector are statistically independent. All components of the feature vector are statistically independent. That means this anyway we discussed in the previous class also. You would be getting covariance matrix effect of it and the Gaussian distribution we have plotted. So what kind of isocurves will you get for these kinds of distributions?
Circles.
Correct. Circles, simple circles is what you are going to get there. Suppose if my diagonal elements are different, sigma I1 square and sigma I2 square, if I write it, then what will I get? What would be the shape of my isocurves?
Ellipse.
Ellipse. Very good. Suppose if I have the off diagonal elements non-zero, what would be the shape of my isocurves?
Ellipse at an angle.
Right, correct. Very good. Now, with that background, with these things, let us try to rewrite these equations now. Which equation shall we rewrite? Gij of x bar, or even before attempting at Gij of x bar, let us see what would be the nature of Gi of x bar. Okay. So the decision, one of them itself, Gi of x bar itself, let us take a look at and how does that curve would look like. That's what we will attempt it. Okay. Right. Good. So what we will do now is let us substitute them here and see what is going to happen here to this expression. Gi of x bar is equal to minus 1 by 2 into, yes. So this is slightly rigorous, but do it. It's not, it's just if matrices, simple vectors multiplication and the matrix multiplication. Let us attempt that. X bar minus mu bar whole transpose. What would be that value here? X bar minus mu bar whole transpose. Or let us do one thing. Before substituting those vectors, let's multiply things together. And then let's make an attempt there. Well, this, okay, when I am multiplying a 2 by 2 matrix, okay, can I write this? How can you represent it as some multiplication with an identity matrix I would like to do? How do you then write it as sigma I? All I want to do is I want here 1 0 0 1. What would be the multiplication factor there?
Sigma I square.
Yeah, sigma I square, that's all. Okay, so you could notice that if you substitute that matrix here, anyway, that if you multiply with x bar minus mu I bar, you are left with just that multiplication factor of sigma I square there, correct? That is all you are left with. Again, I made a small mistake here. Can anybody tell me there is some mistake in this equation, fi of x bar, this equation? Can any of you identify and tell me? I realized it just
Sigma
now.
I inverse.
Correct, very good. This is inverse. That was the mistake. Please correct that. Right. So now, can I not write this as 1 by 2 sigma square into 1 over 2 sigma minus 1 by 2 into 1 over 2 sigma square into x bar minus mu I bar whole transpose into x bar minus mu I bar, right? Can I write it like this? Then of course I have natural logarithm of probability of omega I, and plus this is anyway a constant, okay, for a given class. It doesn't, so of course natural logarithm of p of omega I is also a constant, and of course, yeah, maybe for the time being I'll just put it there without much fuss. Determinant of 1. Okay, so now let's write this up further. How can I further expand this? X bar whole transpose into x bar. So what I'll instead do here is, let me first apply this transpose. So that will be x bar whole transpose minus mu I bar whole transpose, this whole multiplied with x bar minus mu I bar. Let me do the multiplication now. What will be that value? X bar whole transpose into x bar minus, now I'm multiplying the first term x bar whole transpose with the second term there. So that will be mu I bar minus mu I whole transpose into x bar plus, of course, there is these are vectors here. So mu I bar whole transpose into mu I bar. Hope you all agree with and clear with the way I have just written the multiplication that is there in that square bracket. Okay, so then I would like you to comment on these two values of this function versus this function. Is there any relationship between those two functions that I marked there? X bar whole transpose into mu I bar on one side, mu I bar whole transpose into x bar on the other side. X bar and mu bar are vectors of same size. How are they related then?
Both are equal.
Very good. Can you tell me why? First tell me what is the dimensionality of x bar whole transpose times mu I bar when you have x bar of size 2 cross 1 and mu bar is also of 2 cross 1. What is the size of x bar transpose into mu I when they are vectors?
1 by 1.
Correct. Very good. This is 1 cross 1. And what about this? This is 1 cross 1. You just notice here the respective elements of the same indices are getting multiplied and summed up. So both of them are equal. Right? If you still have a doubt, I have already given you the vectors here for x bar and mu I bar. Okay. Just multiply them by taking the respective transpose values and see what is going to happen. Okay, that's a very, very simple. Yet this is something you need to keep in mind all the time. Or later, while we go to other topics and chapters also, you will come across these kinds of simplifications we will be doing or manipulations that we will be doing. So this I would now write x bar whole transpose times x bar, both are equal. So I would write here 2 times mu I bar whole transpose into x bar my plus mu I bar whole transpose into mu I bar. This is what I got here. Okay. This is getting multiplied with minus of 1 over 2 sigma square. Let me also do that. Substitute it there. Gi of x bar is equal to minus 1 by 2 sigma square into x bar whole transpose into x bar. Okay. Then plus 1 by sigma square, because this 2 and 2 gets cancelled, minus and minus will become plus into mu I bar whole transpose into x bar. Okay. Then what? Again, minus 1 by 2 sigma square into mu I bar whole transpose into mu I bar. Then of course I have natural logarithm of probability of omega I. Then I have minus 1 by 2 natural logarithm of the determinant of omega I. This is my Gi of x bar. Okay. Write it further. Let us substitute now the values that we have taken, x bar being x1, x2, mu I bar being mu I1 and mu I2. Let us substitute there and see what kind of equation we are getting here. Gi of x bar is equal to Gi of x bar is equal to minus over 2 sigma square into, what is the value here? X1 bar transpose x bar. What is the value there? What is
Magnitude
x?
of x mod x.
Yeah, please tell me that in terms of x1 and x2.
X1 square plus x2 square.
That's all. Very good. X1 square plus x2 square. Okay. Since anyway I have written minus over 2 sigma square outside, let me keep that in that manner itself. So then let me write here minus 2 times. Now you tell me what would be the value for, I'm done with the first term. The second term you tell me mu I transpose into x bar. What would be that value? You tell me. You take mu I bar transpose. Okay. And then multiply it with x bar and tell me what will I get?
Mu
Minus 2
I1
into,
x1
that's all. Mu
plus 2.
I1 x1 plus mu I2 x2. Okay. Right. This term is done. Then anyway, minus 1 by 2 sigma square I have taken. Now you tell me for mu I transpose mu I. You apply the same logic there. Okay. This is very simple. You apply the same logic there and tell me what would be the sign, negative or positive? First thing first, positive. Now you tell me mu I transpose times mu I. What is that value?
Mu I1 square plus mu I2 square.
Right. I have few more terms which are kind of constants now for a nothing to do with omega I, which is natural logarithm of probability of omega I minus 1 by 2 natural logarithm of determinant of sigma, that sigma I is what I get there. Now, in terms of x1 and x2, these are all, see, this term is a constant here. You could see here for a given sigma I. This term is a constant. You simply tell me this first. My x bar is x1 and x2. My x bar is, let's say, I have already considered that x1 and x2. Okay. This has x1 and x2. Now, what kind of shape can I expect here for varying values of x1 and x2? What could be the shape of this gi of x bar, which is representing kind of one class there? Later, of course, you would look at other classes, but what is the shape of this? Is it a straight line for varying x1 and x2? Is it a circle? Is it a parabola? What all are the possible things here? Hello?
It can be all of those.
Correct. Very good. Because you see here x1 square terms, x2 square terms here. So each of them individually, these gi of x bar, these discriminant function can take, this is referred to as the shapes that it could take or referred to as quadrics, QUADRICS. Quadrics means any quadratic equation that includes ellipsoids, right? Because x1, so that shape, if you look at it, x1, x2, you take it and you draw it. So it's in the three-dimensional things, parabolas, hyperbolas, all these shapes it can take. Okay. Now, next question to you is, with this question, I'd show you some illustrations and yeah, maybe time is running out. So Gj of x bar, if I take now, Gj of x bar I have taken. Now, I want this to be a plane. I don't want a quadratic nature there. So can you tell me what I should do with respect to this? What should be the characteristics of my covariance matrix sigma I and sigma j? Further, what should be the further assumptions I should make such that my decision plane, which is nothing but gi of x bar minus gj of x bar, will be a plane or a hyperplane, not a quadratic nature? What is the assumption that I should make here? Anyone? In other words, I need to get rid of these square terms here. Okay, for a given x bar. How can I do that? Where you have the freedom to tweak the covariance matrices. Okay, maybe I will leave you with this question, and then we will see it in the next class. Sorry.
Hello. Sir, there is
Yes.
a small correction here.
Yeah, please.
Gi of x, if you just see this term, sir, mu I1 of x1 plus mu I2
Right.
of x2, sir, not square.
Which one? Mu I1 of? Yeah, you're right. Correct. Good. This, there is only this 2 I should have written down here, right?
In subscript, yes.
Correct. Very good. Yeah. So hope my question is also clear to you. I want a plane which do not have a quadratic nature. You have given freedom to play with your covariance matrices of I and J. So by giving which values of that you would get a plane, or here it could be in a one-dimensional case, it could be a straight line. Okay, that's the question I am leaving you with. And please do go through this again, your notes, and also I'm following almost the same flow in the textbook. So please do follow that properly and get back to the class on Wednesday. So that if you, it is better by that time you come prepared with what has been already discussed. Otherwise, it looks like a little bit more complicated than what it is. It does have some rigor, but it is very much required to get any insights and interpretations. Only from these equations we'll be able to make some interpretations that you will see in the coming 1 or 2 classes. Okay, I'll stop here. Bye. Take care.